You ever think about what's lurking deep inside your computer's operating system? Well, today we're going to crack open the Linux kernel and find a whole bunch of hidden ciphers.
All right, let me start with a question for you. What if your computer's OS had this massive, sprawling library of cryptographic tools, but it only ever actually used one of them? I mean, that sounds kind of strange, right? Maybe even a little risky. But believe it or not, that's pretty much what's happening. And we're going to figure out why.
Okay, so to get why this is happening, we've got to start with the theory, the big idea. See, on paper, Linux has this system that's all about giving you options, a ton of flexibility when it comes to cryptography.
And that system, it's called the Linux Crypto API. Think of it like a central plug-and-play hub for anything and everything crypto. The whole point is that any other part of the kernel, whether it's managing your hard drive or your network connection, can just tap into it and get top-notch encryption without having to worry about all the nitty-gritty details.
And the thinking behind this API was, well, it was super ambitious. The goal was to hide all the complicated stuff, stop developers from writing the same code over and over, and the big one was to achieve something called crypto agility. Now, that's a fancy term, but it just means you should be able to easily swap out an old, maybe broken encryption algorithm for a brand new, stronger one, to keep the whole system safe for the future.
So what did that philosophy give us? A huge list of available ciphers. We're talking the big one, AES, of course, but also a bunch of others that sound like they're straight out of a spy movie. Serpent, Twofish, Camellia, Blowfish, and a whole lot more. So, in theory, a developer has this giant menu to pick from.
But you know how it is. Theory is one thing. Practice is often something else entirely. So where does all this powerful crypto stuff actually get put to work? Well, it really matters in three main spots. First, you've got disk encryption with tools like dmcrypt. That's what protects your entire hard drive if, say, your laptop gets stolen. Then there's file encryption using fscrypt for locking down just specific files and folders. And finally, you've got network encryption, things like IPsec, which secures your data as it's flying across the internet. And guess what? All three of these super important jobs depend on that very same crypto API. Okay, so let's recap. We have this giant library of choices, and we have these really critical systems that need them. And this is where the plot twist comes in. Because when you stop looking at that big theoretical menu of options, and you start looking at what the security pros actually recommend and what the system defaults to, a totally different picture starts to take shape. And yeah, this table pretty much says it all. For your disk, for your files, and for your network, the default, the one that's recommended every time, it's AES. All those other ones, Serpent, Twofish, sure, they're supported, but you've got to actively dig into the settings and choose them. Nobody does. So that leads us right to the big question, right? Why go through all the trouble of building this super flexible system with all these choices just for one algorithm to completely take over? What's the deal with AES? Why does it rule them all?
Well, the answer isn't really about the lofty software ideals of choice and flexibility. Nope. It all comes down to the cold, hard reality of the computer chip itself.
The secret sauce is something called hardware acceleration, specifically a feature called AES-NI. See, modern processors from Intel and AMD have special instructions baked right into the silicon, and these instructions have one job, and one job only: to run the AES algorithm and to run it insanely fast. And the difference this makes, it's just staggering. I mean, look at this. You've got ciphers like Serpent and Twofish just running on software. They're good, they're secure, but they're kind of plodding along. And then you have AES, using its special hardware instructions. It's not just a little bit faster, it's a night and day difference. It's a colossal leap.
Just how much faster are we talking? Well, we're talking up to 10 times faster. That's not just a small tweak. That is a total game changer. It's the difference between encryption slowing your whole computer down and it being so fast you don't even know it's there.
And that incredible speed, it has a huge ripple effect. That massive performance boost is literally the reason we can have encrypt everything by default turned on for everyone. All of a sudden, speed itself
became a security feature. Because if encryption is fast enough that nobody notices it, you can just turn it on for everybody. And instantly, the security of the entire digital world gets a massive upgrade.
So, all of this brings us to this really interesting debate, a kind of philosophical clash right at the heart of software design. And it's a debate that's happening right inside the Linux kernel.
On one side, you have that crypto agility idea we talked about. It's flexible, it's future-proof, but it's also more complex, which means there are more places for things to go wrong. On the other side, you have a totally different approach called opinionated design. A great example is the WireGuard VPN. It says, nope, no choices. It uses one and only one carefully chosen set of ciphers. It's super simple, easy to check for bugs, but it's completely inflexible if a problem is ever found in that one choice. And what's really wild is that the Linux kernel today actually has both of these competing ideas living side by side. So what's the big takeaway here? Well, first off, in tech, cold, hard reality, especially hardware speed, almost always beats a beautiful theory. That giant list of ciphers in Linux, it's not really a menu you're meant to order from. It's more like a cryptographic museum full of historical relics. For pretty much anything you're going to do today, AES is the answer, plain and simple. The whole system, from the chips to the code, is just built for it.
And that leaves us with one last really important thought.
AES, thanks to that hardware boost, absolutely won the battle for today. But technology never stands still, right? The next big fight on the horizon is against quantum computers. These things threaten to smash our current encryption to pieces. So the real question isn't which of these old ciphers we should use, it's what brand new kind of cryptography are we going to invent to survive in the quantum era?